In part one, I introduced symmetrical components, some like definitions and so on and so forth. But in part two, I'll show how you can use symmetrical components to solve some problems. So for instance, in example one, we have a balanced line to neutral voltage, balanced line to neutral voltages with ABC sequence. So given the line to neutral to line voltages below, assuming balanced line voltages and counterclockwise ABC phase sequence, what are the phase sequence components? Meaning zero sequence, positive and negative sequence. So here are the line-to-line voltages. So the voltage across AB is 208 volts, BC is 208 volts, and AC is. So the first thing we need to do is, since we're going to work with symmetrical components, we need the line to neutral voltages. So the line to neutral voltage is the line to line voltage divided by square root of 3. So 208 divided by root of 3 is 120. So phase A to neutral voltage is 120. Since they are balanced, so if I use A as a reference, I'm given at 0 degrees. I know they are apart by 120 degrees. So I'm assuming ABC. So A is here, B will be here, because if A, again, if I draw a line here, A will cross this line first, then B, then C, and they're apart by 120 degrees. So from part one on symmetrical components, I showed that the zero sequence voltage is equal to 1 over 3 times the sum of the three line to neutral voltages. So then if I just replace them with their quantities here, and if I carry out the calculation, I get 0, which should be expected because the problem statement says balanced ABC, which means it's positive sequence. So that means I should not see zero sequence or negative sequence components. I should only see positive sequence. So let's see if we can see that. V1 is 1 over 3 times VAN plus operator A. And if you remember from part 1, A is equal to magnitude of 1 with an angle of 120 degrees, basically, times VBN plus A squared plus times VCN. So if I carry out, so here's VAN. So here's VBN times operator A. That's why I'm adding 120 degrees here. VCN times A squared, it's because A squared is 1 angle of 240 degrees. So if you carry out the calculation, you get 120 volts with an angle of 0, which is equal to VAN, which should be expected because I have balanced line to neutral voltages with ABC sequence, positive sequence. So I do the same thing for negative sequence current. 1 over 3 times VAN plus A squared times VBN plus A times VCN. So if I carry out the calculation, I get 0, which is expected. I would recommend watching part 1 on symmetrical components if you want to see like these equations basically. For zero sequence, positive sequence, and negative sequence, like how they are derived. So in this example, we see that a three-phase balanced system with ABC phase sequence, there is no negative or zero sequence components. We saw that V, the positive sequence voltage, was equal to the phase A to neutral voltage, and the negative and the zero sequence were zero. Now let's look at another example. I have a load that's connected as a grounded Y with balanced, so I have balanced, but in this time it's ACB sequence currents. So given the balanced line to neutral currents below, assuming phase sequence ACB sequence, what are the phase sequence components? So phase A current is 1200 with zero angle. B phase is 1200 with 120. And C phase current is 1200 with minus or negative 120 degrees amps. So if I draw the sketch here, so here's phase A is at 0 degrees. B is at 120, which means it's this way because I'm assuming counterclockwise rotation. And C is at minus or negative 120 degrees. So this is negative sequence, if you notice here, because if I draw a line and as they rotate counterclockwise, A will cross first, then C will follow it, then B, so it's ACB. So this is negative sequence and it's balanced. So I should only see negative sequence current. Zero sequence and positive should be zero. So these are just general notes. For grounded Y connection, a line-to-line current is equal to a line-to-neutral current. When dealing with symmetrical components, all phasors are line-to-neutral or line-to-ground. Currents in phase A, phase B, phase C are phase neutral. That is A to neutral, B to neutral, and C to neutral. So again, from the equation of zero sequence, I would recommend watching part 1 of symmetrical components, which shows how to use these equations. So if I just plug in the numbers, I get 0. So the zero sequence current is 0. That's because they are balanced. So positive sequence, I do the same thing. Here's the equation. So if I plug in the numbers, I get 0. Again, it's balanced and it's ACB, meaning it's negative sequence. So there should be only negative sequence current. So if I do the same thing, here's the equation. And if I carry out the calculation, I get I2 or negative sequence is equal to phase A current. So in this example, we said that balanced three-phase systems with ACB or negative sequence have no zero sequence or positive sequence components. So here's another example, example 3. We have a three-phase feeder serving a balance. So I have balanced grounded Y load with an open phase, in this case C. So given the unbalanced line to neutral currents below C phase, because C phase is open, assuming counterclockwise ABC phase sequence, so I'm assuming positive sequence, ABC, yeah, positive sequence rotation. What are the phase sequence components and the neutral currents? So here are the currents. Current in phase A is 600 amps with an angle of 0 degrees. Phase B current is 600 with negative 120 degrees, and phase C is just 0. So basically, this is a grounded Y. So if I call them phase A, phase B, phase C, and here's their neutral, which is grounded, but phase C somehow is open. So I'm just gonna erase this. So phase C is open. So if I draw the phasors here, phase A current is 600 amp at 0 degrees, then B is at negative 120 degrees. So again, if we do the same thing, so zero sequence current, and I basically plug in the numbers here, so I get 200 amps with an angle of minus or negative 60 degrees. The positive sequence current, here's the equation, then I just plug in the numbers basically, and just remember operator A is equal to magnitude of 1 and angle of 120 degrees, and A squared is equal to magnitude of 1 and angle of 240 degrees. Basically, if you multiply, like in this case, phase B times A, it will rotate it counterclockwise by 120 degrees. It does not change its magnitude. And if you multiply it by A squared, it will rotate it by 240 degrees. So that's what A or A squared does basically. So I get 400 amps with an angle of 0 degrees. If I do the same thing for negative sequence current, I get 200 amps with an angle of 60 degrees. And we know the current that would flow in the neutral is the sum of the phase currents, because if this is a neutral, so if you have phase A, phase B, but phase C is open, so IC is just 0. So the current that will flow through the neutral is the sum basically, provided it's grounded. If it's not grounded, there will be no current flowing through the neutral. So then if I just plug in the numbers, I get 600 amps with an angle of negative 60 degrees, which is, notice, which is 3 times I0, which is 3 times this here. So if you have a grounded Y, a grounded Y, meaning a Y connection with grounded neutral, the current that will flow through the neutral is 3 times the zero sequence current. So we see that unbalanced three-phase systems with ABC positive sequence, in this case, it has zero sequence, positive sequence, and negative sequence components because none of them were zero. Also, in unbalanced scenario, current will flow in the neutral if it's grounded. And if you know the equivalent sequence impedances, you can calculate the sequence and phase voltages. So as you can see, these examples show how you can use symmetrical components to calculate the sequence currents. And you can also use symmetrical components if you have line to ground, basically different faults, which probably will be another topic for another video. So these are just some general notes. Delta and ungrounded Y connections, now zero sequence current will flow. Basically, they block the zero sequence current. So in general, you have to have a path through the ground for the zero sequence current to flow. In a balanced system, or in a balanced three-phase system, positive sequence currents will only produce positive sequence voltage drops. Negative sequence will only produce negative sequence voltage drops. Zero sequence currents will only produce zero sequence voltage drops. And we saw that through the examples that I went through. In unbalanced system, unsymmetrical faults, basically line to ground, line to line to ground, open phases, line to line, open phases, etc. Positive sequence currents will produce positive, negative, and possibly zero sequence voltage drops. Because I said possibly zero sequence, because a line to line fault, if it does not involve a ground, there will be no zero sequence, but you will have positive and negative sequence. A line to ground or line to ground, you will have zero sequence. And if you have a neutral that's grounded, it will flow through that neutral. Negative sequence currents produce positive, negative, and possibly this zero sequence is the same basically. Zero sequence currents will produce positive, negative, and zero sequence voltage drops. I hope this video helps or provide good understanding how to use symmetrical components to calculate sequence currents due to imbalance, that occur due to single phase loading, for instance, or an open phase, in a three-phase system. And as I stated, possibly in future videos, I will do a video on how to use symmetrical components to solve fault current problems, like line to ground, line to line, line to line to ground, and so on and so forth. Thank you and have a great day.